Hello everyone, welcome to my class. Today we will continue with concept of coherence. In the last class we talked about temporal coherence and the corresponding coherence length, and in this topic we talked about two experiments. The first one is Young's double slit experiment and the second is Michelson interferometer. Today we will touch the other category of coherence, which is spatial coherence. As discussed in the last class, it is related to the finiteness of the source, finite dimension of the source in space. Yeah. Now, begin with the same experiment which we discussed in the last class for temporal coherence, which is our Young's double slit experiment. Now, here instead of taking one source S from which we generate two sources S1 and S2, we will take two sources S and S prime, and S prime is assumed to be displaced linearly. Linearly means it is displaced vertically by a length L prime from S, as shown here in this figure. Now, it is also assumed that S is nearly monochromatic and therefore, it produces interference fringes of good contrast on this screen P P prime. Okay. Now, O is a point which is at the center of the screen, which is at the axis of the symmetry. Therefore, S1O, this path length would be equal to S2O. Okay. And therefore, the point source S will produce an intensity maximum around point O. Now, the next source which we name as S prime, which is at a distance L prime from S. For this particular source, we assume that it does not have any definite phase relationship with source S. It means S and S prime sources are incoherent. Okay. Therefore, the interference pattern observed on the screen will be a superposition of the intensity distributions of the interference pattern formed due to S and S prime individually. Okay. Now, observe the word, it is superposition of intensity distribution, not the amplitude. Why? Because these sources are incoherent. Okay. Therefore, the resultant pattern at the screen would be the sum of irradiances produced by source S and source S prime. Okay. Now, if the separation L prime is slowly increased from 0, okay, initially we assume that L prime is 0, it means that S and S prime are sitting at the same point. Therefore, very beautiful fringes of very good contrast would be observed, but if we slowly increase L prime, if we start displacing the source S prime from S, then what will happen? The contrast of the fringes on the screen P P prime becomes poorer, because the interference pattern produced by S prime is slightly shifted from that produced by S. Okay. Now, we will as L prime would be non-zero, then we will have 2 point sources, and these 2 point sources will produce their independent fringe pattern on the screen, and then we will have to add the 2 irradiances, and therefore, the contrast of the final pattern would be reduced. Okay. Now, if S prime S2 minus S prime S1 is lambda by 2, it means if these rays are such that the path difference is half integral multiple of wavelength, that is they are creating destructive interference, then the minima of the interference pattern produced by S will fall on the maxima of the interference pattern produced by S prime, okay, which is very much clear. Okay. Here S is symmetrically situated, therefore, the distance S, let me pick different color, the distance S S1 is equal to S S2, and therefore, the rays which are reaching at point S1 and S2 from source S, they are in the same phase, they are phase correlated. Now, the second source, which is S prime, since it is not on the axis of symmetry, since it is slightly displaced, the rays which are reaching to point S1 and S2 from S prime, there would be a slight phase difference, and if this phase difference is half integral multiple of lambda, and in this case the minima of the interference pattern produced by S will fall on the maxima of the interference pattern produced by S prime, and this ultimately will give no fringe pattern. A uniform illumination on the screen will be visible therefore. Okay. Now, let us do some geometry. Let us calculate S prime S2 distance. Okay. This is S prime S2. Okay. What would be S prime S2? Now, we know that given the distance between S1 and S2 is d, S prime and S is L prime. This distance is A1, where this ray crosses the axis of symmetry is A1, and this distance is A2, and A1 plus A2 is capital A, which is given here. With this condition, we can calculate S prime S2. Now, if you consider the this right angle triangle, then S prime S2 is hypotenuse, and S prime S2 would be S prime S1 square plus S1 S2 square, and then square root of this sum, and this is what is done here. Now, you can expand it using binomial expansion, and this reduces to this expression. Okay, we can use binomial expansion and neglect higher order term because A is assumed to be much larger than D and L prime. D is separation between S1 and S2, L prime is the displacement of S prime from S. Okay. Similarly, we can calculate S prime S1, which is this length using the Pythagoras theorem, yeah, and this gives equation number 70. Now, once these two distances are known, then to calculate the path length difference, we will subtract equation number 70 from 69. Okay, and then S prime S2 minus S prime S1 can be calculated, and then if you substitute for S prime S2 and S prime S1 from 69 and 70 and do a little bit of mathematics, then you will get this expression, which is L prime D by A. The path length difference is L prime D by A, but the condition with which we start with is that S prime S2 minus S prime S1 is equal to lambda by 2, and if this condition hold, we should not get any fringe. Yeah, let us substitute this expression of S prime S2 minus S prime S1, which is lambda by 2 in equation number 71. This gives equation number 72, and from here we can calculate the expression for L prime, which is the separation between the two sources S prime and S. Okay, and this equation number 73 thus gives this requisite separation. Okay. It means if we have two sources and one is on the axis and one is laterally displaced by L prime with this distance, which is lambda I by 2d, then we will not observe any fringe. Okay. Or if the displacement is larger than this L prime, then too we will not observe any fringe, but if this displacement is smaller than this length, then the fringes will be observed. We will be able to see the fringes on the screen. Now, if we have an extended incoherent source, now we are taking a different case. Till now we consider 2-point sources, but now we are considering a line source. Now, line source means array of point sources. Yeah. Now, we have extended incoherent source whose linear dimension is given by lambda A by d, okay, which is half of L prime. Okay. L prime by 2 is equal to lambda which is twice of L prime, okay, because twice of L prime is lambda I by d. Okay. Now, we consider a extended source which is extending from here to there. This is the length element now. Then from every point on the source, there is a point at a distance of lambda A by 2d. Now, we are following the same thing which we did in the last class. In the last class, we took a source with a particular bandwidth, and we took two wavelengths out of this bandwidth. One is on the one of the extremity and one at the center. Okay, the same thing we are doing here. Here the source width is lambda A by d, and then we took one point here and other point at the center. Okay, these points will be at a distance lambda I by 2d. Yeah, let us do it here. This is the source Okay. Here it is 0, here it is lambda a by d, and here we pick another point which is at a distance lambda a by 2d from first extremity. Okay. Now, this distance is lambda a by twice of d, and this distance is also lambda a by twice of d. Now, for each point source on the first band, let us pick another color. This is your first band and this is your second band. Now, for each point on the first band, we can find a corresponding point in the second band. This is our first band, this is second band. For each point in the first band, we can find a corresponding point in the second band, which is at a distance 2a by lambda. Yeah, because these 2 points are at a distance which are at a distance lambda by 2d. Now, these 2 points are at a distance lambda by 2d. Similarly, let us shift this point here and this point here. This distance is also equal to lambda by 2d. This distance is also lambda a by 2d. This distance is also lambda a by 2d. This distance is also lambda a by 2d. It means for every point on the source, there is a point at a distance of lambda a by 2d, which produces fringes that are shifted by 1/2 of a fringe width. This sentence means that the 2 fringes would be out of phase by 180 degree, means maxima of one will fall on the minima of other, and therefore, the resultant pattern will not be observed. We will have a uniform background therefore. Now, the same thing we did in the spectral domain for temporal coherence, and for spatial coherence we are doing it in space now. Okay. Thus, for an extended incoherent source means extended line source, which we are considering in this analysis, the interference fringes of good contrast will be observed only when the length element is much smaller than lambda a by d. Okay. And this is very much obvious from this analysis. Okay. Now, if theta is the angle subtended by the source at the slit, okay. Now, we are considering this figure, this is the angle theta, then from the figure we can see that L would be equal to theta into A, and therefore, from equation 74 L is equal to theta into A, or theta is almost equal to L by A for very small theta. Then from equation 74, okay, let us replace this L by A in equation 74 with theta, and then we get d must be much less than lambda by theta. Okay. And if d is of the order of lambda by theta, fringes will be of poor contrast. Okay. We will get better fringes if d is much smaller than lambda by theta. We will get poor contrast fringes if d is almost equal to lambda by theta or larger than lambda by theta. Okay. Now, this distance which says that LW is lambda by theta, it gives a distance over which the beam may be assumed to be spatially coherent. Okay. Now, we are talking about the extent, the transverse extent of the beam. Okay. And this says that if it is equal to lambda by theta, we will be able to observe we will see a uniform background, no fringes, and if it is smaller than lambda by theta, we will see good contrast fringes. And this distance LW gives a distance over which the beam may be assumed to be spatially coherent, and therefore, it is referred to as lateral coherence width. Okay. Of course, it is related to the space, yeah, length element, therefore, it is called lateral coherence width. Now, let us dive a bit more deep. Let us talk about the degree of coherence, a bit advanced topic. The complex degree of coherence and fringe visibility, this is the title, and here we will again consider the conventional Young's double slit setup, where we have a source S, out of source S we are creating 2 more sources which are completely coherent, and the fringes are being observed at a screen at point P, which is at a distance r1 from source S1 and r2 from source S2. Okay. Now, suppose that E1 PT and E2 PT represents the complex fields at point P due to the waves emanating from source S1 and S2 respectively. Okay. Some waves emanates from S1 and it is reaching to point P, and another wave emanates from S2 and it is reaching point P again, and these waves are represented by E1 function of PT, E2 function of PT. Okay. P is a position, yeah, the same point which is at screen. Okay. And T is the time at which the fields are observed. Okay. Therefore, the intensity at P will be proportional to mod of E square, where E is superposition of the two complex fields which are E1 and E2. Okay. How to calculate superposition? E would be E1 plus E2, and then we will take complex conjugate of E, and then we multiply the E with complex conjugate of E, and this will give the intensity at a point of observation P, and this is what is done exactly here, and we get equation number 77. Okay. And this can also be written in this form, a bit modified, which is equation number 78. But we know that fields are rapidly varying quantity, particularly in visible range. Therefore, we observe only average value of this field, and we define I1 as time average of mod of E1 square, I2 as time average of mod of E2 square. Okay. And therefore, this equation 78 reduced to this expression, where I is equal to I1 plus I2 plus 2 square root of I1 I2 real part of gamma 1 2. Okay. Therefore, where I is equal to your mod of E PT square here, and I1 I2 expressions are given here. Okay. Gamma 1 2 is given by this expression. It is time average of E1 star into E2 star, so into E2, and in the denominator we have a square root of time average of mod of E1 square and time multiplied by time average of mod of E2 square. They all are calculated at point P, which is on the screen, and at time T, time of observation of this field at point P. This gamma is known as complex degree of coherence, and the terms within this triangles denotes time average. Okay. The field E1 PT is due to waves emanating from point source S1 at some earlier time, and what is this earlier time? This is T minus R1 by C. Okay. Where R1 is equal to S1P, we have already done it here. Done it, therefore, I am not detailing too much on this. Yeah. E1 PT will be proportional to E S1 T R1 minus C, because the fringe pattern on the screen is invariant in time. Okay. And E is the field at point P. Therefore, this field component would be proportional to the field which was at point S1, the source S1, at some earlier time. And what is that earlier time? Earlier time is T minus R1 by C. Okay. Where E1 T denotes the field at S1 at time T. Okay. Similarly, E2 T would be proportional to E S2 T minus R2 by C. Okay. E2 is the field contribution at P due to source S2. Okay. Therefore, the earlier time for this field would be T minus R2 by C, which is written here. Therefore, we can replace since these E1 and E2 are proportional to these fields, then we can replace the expression of E1 E2 in the expression of gamma 1 2. Okay. Doing this, we get a bit complicated expression here, which is given by question number 79. Okay. Now, we are seeing sustained interference fringes on the screen, therefore, overall intensity distribution in fringe pattern does not change with time. Okay. And therefore, instead of writing this complex time, we will just take into account the time difference. Okay. We will subtract these two times and get a time difference tau, and therefore, this equation of gamma 1 to get modified here in expression number 80. Okay. Where tau is the difference in time. Now assume that S, S1 and S2 to be of negligible spatial dimension. We are assuming that they are point sources. Okay. Okay, if S1 and S2 are equidistant from S, means S is here, and from S, S1 and S2 are being generated, and if these distances are same, then E S1t would be equal to E S2t, because the source S1 and S2 which are being generated from S, they will receive the same field, same amplitude, same magnitude of the field. Therefore, E S1t would be equal to E S2t, and let us assume that this is equal to E t. Therefore, the previous expression of gamma 1 2 again get simplified, and this is the expression. Here we have dropped S1 S2 or E1 E2, okay, with much simpler expression. Okay. But actually the field is represented by this quantity, E t is equal to A t e to the power I omega t plus phi t, where A t is amplitude, phi is phi, which are slowly varying function of time, okay, and the rapidly varying function of time is here in the phase part omega t. Okay. For perfectly monochromatic beam, A t and phi t are constant, okay, they does not vary, okay, they do not vary, A t and phi t they do not vary, and therefore, E star t plus tau into E tau, if you want to calculate, they would be equal to A square e to the power I omega t. How? The E star t plus tau from this expression can be written as A and t plus tau e to the power I omega, again it would be t plus omega tau plus phi t plus tau. Okay. But we know that it is a slowly varying function of time A and phi, they will not vary, they are constant. Okay. This, since it is of course, in this case A and phi will not vary because they are constant, it is a monochromatic wave, therefore, it would be A t, and in the phase part we have e to the power I omega tau, and the rest of the function, let us assume that it is I omega t plus phi. Okay. Similarly, for E t, if you want to calculate it, it would be equal to A tau e to the power I omega t, here it is a minus here, plus phi t. Okay. These are the two functions. Now, it is a complex conjugate here, therefore, it would be plus here. Okay. And if you just multiply these two functions, then what you can see is that this function will go away, and we would be left with A t square, because there are two A and e to the power I omega tau, and this is what is given here in equation number 82. Okay. And therefore, the expression for gamma 1 2 would be e to the power I omega t, because in the denominator also we are having E t square, time average of E t square, which is again equal to A tau, A t is A square, and therefore, A square will go away, and the final expression of gamma 1 2 would be e to the power I omega tau. Okay. What I am saying is this, E t square would be equal to the time average A square, okay, which is in the denominator, and in the numerator we have A square e to the power I omega tau, and therefore, the resultant expression of gamma 1 2 would be equal to e to the power I omega t. Okay. And therefore, the final irradiance expression can be written like this, where in the expression of gamma 1 tau, which is equal to e to the power I omega t, which is a complex number, but we are behind real stuff here. Therefore, we take a real part of this function, which is cos omega tau. Okay, it is a tau, and therefore, the final expression of irradiance at point P reduces down to equation number 84, which is I 1 plus I 2 plus 2 square root of I 1 I 2 cos omega t. Now, we will talk about visibility. Okay. I will introduce visibility formally after a few slides, but since it is relevant here in this calculation, I just quickly introduce visibility as I max minus I mean upon I max plus I mean, where I max and I mean are irradiance maxima and irradiance minima in an interference pattern. Now, if you substitute for I max and I mean from equation number 84, we know I max, you will get I max when cos omega t is equal to 0, and we will get I mean when cos omega t is equal to, sorry, we will get I max when cos omega t is equal to 1, and we will get I mean when cos omega t is equal to -1. Okay, with this substitution, the expression of V is given by 86, equation number 86. Now, if the two sources are of equal irradiance when I 1 is equal to I 2, then we have maximum value of visibility V. Okay. And when we maximize it, it implies that for a perfectly monochromatic beam, the contrast of the fringes is perfect. Okay. Visibility, as its name suggests, it tells the contrast. Okay. And when it is 1, then the contrast is perfect. Okay. Now, this derivation, this was for a monochromatic beam. Okay. For monochromatic beam, only A and phi is constant, and then we can write A plus tau, A function of t plus tau is equal to A t, because A t and phi t does not depend on any other parameter, because they are constant in itself. But the general expression for gamma would not be of this form, it is for I omega tau. This is for only monochromatic wave, but for the general case, gamma 1 2 can be written as mod of gamma 1 2 and e to the power I omega tau plus some beta, some phase. Okay. And we therefore, the expression for the irradiance, total irradiance at point of observation, we modifies by this mod of gamma 1 2 into cos alpha, where alpha is given by omega tau plus beta, which is here. Okay. Here in this equation number 87, if you calculate I max and I min, then they will have these expressions, where of course, when cos alpha is equal to plus 1, we have I max, and when cos alpha is equal to -1, we have I min. Now, if you calculate visibility, then you see that in the expression of visibility, apart from this term which was earlier in our previous expression here in equation number 86, we have additional term which is mod of gamma 1 2. Okay. It means once you measure the visibility of the fringes, then this will give the information about mod of gamma 1 2. Okay. And visibility measurement is very simple, just measure the maximum irradiance and minimum irradiance and take their ratio. Yeah, it is given here I max minus I min upon I max plus I min, that is all. Once you measure the visibility, you have the information of gamma 1 2. Okay. And when mod of gamma 1 2 is equal to 1, it implies that the sources are completely coherent. When gamma 1 2 is equal to 0, it means when visibility is equal to 0, it implies that sources are completely incoherent. Okay. And in general, for all sources, mod of gamma 1 2 varies between 0 and 1, and the sources for which mod gamma 1 2 is almost equal to 0.86 or larger, then we call those sources as coherent sources. Okay. Now, coming back to visibility, the quality of fringes produced by an interferometric system can be described quantitatively using visibility V, and the visibility is defined by this term which we already discussed about, and I max I min are the irradiances corresponding to maxima and adjacent minimum in the fringe pattern respectively. Yeah? And it measures the degree of coherence of the light. Okay. This is already defined. Okay. And this concludes everything on coherence, and with this I end my lecture, and thank you for listening me.